All right. Welcome to our Pacific Quasiworld seminar today. So our first speaker is Alex Kapiamba, and he will talk about a priori bounds for some near-parabolic primitive combinatorics. So please.
Yeah, thanks for the introduction, Mario, and thanks for the invitation to speak for you and the other organizers. Yeah, and so I'm going to be talking about some results of these a priori bounds and some MLC results. Probably, I don't know what the full background of everybody is here, so I'm not going to get into too much detail, but going to try and lay the framework of what we've been working on and thinking about, and just how it fits together with some of the other results on MLC. And as I said, some of this, or all of this will be based on joint work with Jeremy Kahn, and some of it will be, I'll mention a little bit, some related work by Jeremy and Misha Lyubich when we get there. All right, but the setup, right, is we're going to be looking at these quadratic polynomials given by z squared plus c, and we have the Phil-Julia set, which is the set of all points where the where our quadratic polynomial are points which under iteration don't go to infinity, or equivalently the points the points where it doesn't go to infinity. So for examples here, we have 3 examples where we can see it can be connected, it can be disconnected in the center here where we get actually a Cantor set, or it can be connected with some sort of interesting topology. And so moving on from these specific quadratic polynomials, we can extend to the parameter space of all quadratic polynomials. And so we're looking at z squared plus c, so we can consider the set of all parameters c. And it turns out there's a dichotomy on whether or not the Phil-Julia set's connected, or whether or not the critical point 0, the unique critical point is z squared plus c, is inside the Phil-Julia set. So when you draw that picture, you get the Mandelbrot set here. Just to be clear, the Mandelbrot set is all the points in black, and then all the blue points here are points which are outside the Mandelbrot set. And so this fractal was sort of first popularized by Mandelbrot back in the 70s, and has been the study of a lot of analysis and a lot of theory has gone into understanding the geometry of this fractal object. And there's actually quite a lot that we're able to say about it. And we know a lot about the structure of this fractal, but there's still one main conjecture about its geometry, or really its topology, which has remained unsolved for the past 40 years, which is whether or not it's locally connected, which is usually abbreviated as the MLC conjecture. And so the first really breakthrough theorem towards the MLC conjecture, which has sort of been the starting point for a lot of the theory since, was by Yokos, where he proved that if you have a polynomial which isn't infinitely renormalizable, which I'll explain what that means, then we do have local connectivity at those parameters. And so it's actually a funny story. Apparently, when Yokos' result was first proved, there was a lot of excitement and people thought, okay, we're almost done. MLC is almost resolved. We just have this sort of rare, sort of bizarre, infinitely renormalizable cases to understand, but they can't actually be that complicated. And so hopefully we should be able to solve it pretty quickly. And this was back in the 90s, I believe. And so since then, it turns out this infinitely renormalizable case has been quite complicated and quite difficult to understand. Okay, and so moving on to sort of what is this infinitely renormalizable? First we got to talk about what renormalization is. And so in this context, the renormalization corresponds to quadratic-like renormalization. And so a quadratic-like map is just a map which maps some disk analytically as a branch cover of degree 2 onto a larger disk, and it's proper. And in particular, we require that the smaller disk is compactly contained in the larger disk. Right, and so anything that exhibits this behavior is called a quadratic-like map, which doesn't necessarily sort of immediately look like quadratic polynomials, but it turns out these are intimately related with quadratic polynomials. For these quadratic-like maps, we can define an analog of the Phil-Julia set, where for polynomials, we had points which don't go to infinity. So we can think about that as points which don't sort of escape to infinity. For quadratic-like maps, we similarly want to think about the Phil-Julia set as being points which don't escape. And here, escaping is just leaving the domain, right? We have some finite domain, and if we if it stays inside the domain, if we can keep iterating it for all time, then it's inside the filled Julia set. And just a little notation that we're going to use later is that when we have a connected filled Julia set, we can define the modulus of this quadratic-like map. And the modulus of this quadratic-like map is just given by the modulus of the annulus, where you take your domain, or I guess your codomain, and then cut out the filled Julia set. So this gives you some measure of sort of how much space you have around your filled Julia set. And the sort of prototypical example is that if you have any quadratic map or quadratic polynomial, if you take a very, very large disk centered at 0, as long as it's sufficiently large, and you push it forward, it's going to map to a disk which is larger and contains itself, because we essentially are mapping by z squared to a large disk. And so this will give an example of a quadratic-like map, as I sort of have shown in the picture here. And the one thing that we can observe from this, which is one of the sort of technical details we need to be careful of, is that if I have this quadratic-like map, or a quadratic polynomial that I'm restricting to a quadratic-like map, the modulus of the quadratic-like map isn't well defined in terms of the polynomial. If I pick different restrictions, I'll get a different modulus. If I take a really big disk, the modulus of my annuli might change. And so there's sort of some technical details about how do you define your restriction, which I'm going to mostly try and sweep under the rug, but it's something to keep in mind that in general, you need to be sort of careful when you're looking at these quadratic-like maps and how you define them, because given any quadratic-like map, you can find some restriction with smaller modulus. And so generally, when we think about these quadratic-like maps, we're going to want to sort of imagine being able to vary the domain or take sort of the biggest possible one. And so formally, this is called quadratic-like germs, but I don't want to get too much into the theory. But in case you're curious, there's sort of a well-developed theory in understanding this phenomenon. But moving on, the 4 quadratic-like maps, a very important theorem of Doherty and Hubbard, also called the straightening theorem, is that if you have a quadratic-like map, it's hybrid conjugate to some quadratic polynomial, some actual quadratic polynomial. And here, if you're familiar with hybrid conjugate, this is quasi-conformally conjugate, where the dilatation is 0 almost everywhere on the filled Julia set. So you can just mostly imagine that it's QC conjugate. It's a little bit stronger, which for our purposes, we won't really use. But in general, it's a little stronger than quasi-conformal. And in particular, if you have something where if you have a quadratic-like map where the filled Julia set is connected, then the quadratic polynomial that you're hybrid conjugate to in the family z squared plus c, it's unique. And so you can really identify it with a unique point in the Mandelbrot set. And so with this definition or this hybrid conjugacy and this straightening, we get this definition of renormalization or quadratic-like renormalization, which is if we have a quadratic-like map, we'll just say that it's renormalizable if when I take some iterate of the map, some iterate larger than 1 specifically, you get a restriction which is also itself a quadratic-like map. And so here I have a picture of some quadratic polynomial, where here if I take this sort of black disk in the filled Julia set and take some disk around it, when I map it forward, it maps to some other disk. When I map it forward, it maps to another disk. And then under the third iterate, it returns to a larger disk containing itself. So in this case, the third iterate gives us a new quadratic-like restriction, and this restriction gives us a means, right? What this means is that our map is renormalizable. And this, in particular, this restriction, I'll call the A renormalization of this. The renormalization isn't necessarily unique. As I mentioned before, there might be different domains I can pick, but also something might have different renormalizations. There might be some other disk living inside this filled Julia set, which is being mapped over itself under some number of iterates, which a priori could be totally unrelated. All right, and so so this is something which is renormalizable.
So a quick question related to what you said, right? I mean, in this case, you have this period 3, right? And I guess you could also renormalize on these small disks on the left and the right. Is this correct?
Yeah. So in this case, I mean, so for this example that I've drawn here, around this disk, if I try and look at a further renormalization, the only iterate I'll get is period 1. And so that won't give me a renormalization. So for this particular example, I don't get any extra renormalization. But it's possible, I mean, besides may say changing the domain. If I move this disk a little bit, then I will also get a quadratic-like
Well,
restriction.
my question was, I mean, if you look, for example, this small disk in your picture on the very left, right?
Yeah. Oh, yes.
This
yes.
could also use
Thank you.
to renormalize the map there, right?
Yes. Sorry, that's a good point. Yeah. If I look at this disk here, as Mario says, this disk will map over here, which will map to this large disk here, which will map to some other disk around this. And so I also get some renormalization corresponding to sort of this disk here, or another renormalization corresponding to this disk here. Usually it's nicer to just to fix a particular one when we have a cycle like this, to only consider the renormalization that contains the unique critical point, which you can totally handle. But this is also sort of already hints at the fact that if we wanted to go to higher degree polynomials where we have many different critical points all interacting, then the situation gets much more complicated. But for now, we're just going to be looking at these quadratic polynomials. Okay, and so with these, right, so as I said, we have this renormalization. And so going back to Yocos's theorem, right, the only issue is that the only obstruction to local connectivity will be maps which are infinitely renormalizable. And so we can imagine, right, we have this quadratic polynomial, which gives us a quadratic-like map. And instead of this picture, we could imagine the quadratic-like map that we get is itself renormalizable. And then that will give us a new quadratic-like map, which could again be renormalizable, and so on. And so, right, infinitely renormalizable just means that I can repeat this process infinitely many. Every time I take these quadratic-like restrictions, I can find a further quadratic-like restriction, which is also renormalizable. And so this is exactly sort of, well, not necessarily an obstruction, but an obstruction to at least Yocos's proof of local connectivity. But conjecturally, local connectivity holds everywhere. So it's just a matter of understanding and controlling these different cases. Okay, and so in the realm, Yocos sort of restricted our attention to the infinitely renormalizable case. And one of the first major results for the infinitely renormalizable case was by Misha Lyubich, which says that if I have an infinitely renormalizable polynomial that has what are called a priori bounds and satisfies the secondary limbs condition, then you have MLC. And so the first one, the secondary limbs condition, is a condition I'll talk about in a little bit. It takes a little bit more to get into, but the a priori bounds we can get to sort of directly. And so a priori bounds, we look at some quadratic-like map, which I'm calling G0. And this has a priori bounds if we can produce some renormalizations. So here I want, so G0, I start with my map G0. G1 is some renormalization of G0. It's some corresponds to some restriction of some higher iterate. G2 corresponds to some renormalization of G1. G3 corresponds to some renormalization of G2, etc. So I get this infinite sequence of quadratic-like maps. And this has a priori bounds if these renormalizations, all the moduli of all of these quadratic-like maps is uniformly bounded. There's some epsilon so that all of these quadratic-like maps have modulus at least epsilon.
So one quick question here. In your definition of modulus, right? I mean, there was this domain V, which was not kind of unique. So
yes.
the V here for each GN will have its own VN, or how does it work here?
Yes. So each G, so these renormalizations come equipped very like here you really need to explicitly give them a choice of domain and codomain. And so I've sort of set it where we can this is just saying that we can pick them in some way where we get these bounds. But yeah, and there's other ways of stating it where, like, if I look at for these different renormalizations, I could take like the soup of all possible restrictions corresponding to some renormalization and ask that these soups give me some sort of like canonical, like trying to form some version of a canonical modulus, and then just asking, then you can really define it just combinatorially rather than having to pick a particular restriction. But there are ways to sort of massage around it, but require sort of a little bit more technical detail. But yeah, this is, as I mentioned right there, one of the things you have to be very careful of is the fact that all of these domains are not really uniquely defined when I have these renormalizations. And so you have to be very careful sort of playing with it and maneuvering around in order to ensure that all of your statements are sort of carefully and correctly given. Yeah, and I even reminded, right, it's really important to keep in mind that these aren't unique. But oftentimes, and this is one of the things that Jeremy developed, there's ways of trying to sort of get like some kind of canonical renormalization to simplify these, but then you have to leave the world of quadratic-like maps into what he calls pseudo-quadratic-like maps, which is another story, which I'm happy to talk about, but maybe we can postpone that. We'll see how much time we have. All right, and so this result of Lyubich was sort of the first thing that, and Lyubich was able to, in his example, or I guess in his paper on this, he proved some a priori bounds for some kinds of combinatorics, or some kinds of infinitely renormalizable polynomials, to give some examples of infinitely renormalizable polynomials which have MLC at the corresponding parameter. And so equipped with this result, sort of one of the main questions in the infinitely renormalizable case is how to establish these a priori bounds and how to show that you can find these renormalizations that all have some definite space in between the filled Julia sets. Where here, I guess I don't think I have a slide on it, but just to give a sense of exactly what goes into this proof and why the a priori bounds matter. What Misha does is he shows that if you have a priori, what you want to say is that if you have two maps with the two infinitely renormalizable maps, you want to show that if they have the same combinatorics, maybe I'll actually, let me postpone that to once I define combinatorics, and it'll be easier to sort of state carefully. But so, yeah, so here, in order to describe and really characterize the different kinds of infinitely renormalizable combinatoric or maps, it's nice to have some combinatorial description of them. And so in order to get...
You can say that you're showing the rigidity from this a priori bound.
Yes. Yeah, the a priori bounds, give specifically a rigidity statement where the space in between the annuli really gives you room to do quasi-conformal surgery and to do some sort of, gives you space to work with quasi-conformally, and this space will give you a rigidity statement, and then with the rigidity statement, you get local connectivity. Yes, and so in order to combinatorially characterize these different maps, these infinitely renormalizable maps, we can look at what are called small Mandelbrot sets, which are just subsets of the Mandelbrot set, which are homeomorphic to the original one, in particular homeomorphic according to some straightening. Right, and so here I want some neighborhood, some open set where nearby I get quadratic-like restrictions, all of the same period. And these quadratic-like restrictions all depend analytically on my parameter in this neighborhood around this set. And the corresponding straightening map, this Doherty and Hubbard straightening map, gives me a homeomorphism from my small Mandelbrot set to the larger Mandelbrot set. So just as an example here on the left, I have inside the Mandelbrot set a smaller version of the Mandelbrot set, and which we can sort of plainly see. And every parameter near here corresponds to some quadratic-like restriction. In this case, this is exactly it's called the airplane combinatorics, this period 3 combinatorics that we saw earlier. So all of these maps give us some quadratic-like restriction. In particular, the small Mandelbrot set we see here corresponds to where we have a renormalization. So this quadratic restriction has connected filled Julia set. And this kind is called primitive, where it has a cusp. And in particular, one way of seeing this is that all of the small filled Julia sets, all the filled Julia sets of the renormalization, which I guess just to go back to this picture, right here inside for these renormalization, we have small filled Julia sets. And these small Julia sets are all disjoint, right? They're really staying far apart, which gives us this cusp and gives us the primitive case. In the satellite case, where here it doesn't look as plainly as a Mandelbrot set, but we can see it gives us a small copy of the Mandelbrot set, except now instead of having a cusp, we have a smooth point corresponding to the point z squared plus a quarter. And this is called satellite. And in the satellite case, our small Mandelbrot set copies are, instead of being disjoint, they're all going to touch at some point. And it turns out this touching really complicates the analysis. And so it for a long time, the primitive case has been easier to understand, but recently there's been some progress in understanding the satellite combinatorics. And so we will talk a little bit about the results there. All right, but with these combinatorics, or with these definitions of small Mandelbrot sets, right? These are just, again, small copies of the Mandelbrot set inside the small Mandelbrot set, corresponding to some family of renormalizations. If we have some sequence of small Mandelbrot sets, we will say that an infinitely renormalizable map, which has renormalizations given by some sequence of quadratic-like maps, has the combinatorics given by this sequence. If each of these quadratic-like maps is hybrid conjugate to a map inside these small Mandelbrot sets. Right, so each quadratic-like map from the straightening theorem can be identified with some polynomial inside the Mandelbrot set. And then we just want every time we get this quadratic-like restriction, we want the corresponding polynomial to be inside our given small Mandelbrot set. Right, and so here as we go from one small Mandelbrot set to the next small Mandelbrot set to the next small Mandelbrot set, this is telling us exactly where our renormalizations are living. And sort of as an example here, we have this Mandelbrot set here with a small Mandelbrot set given by here, and then we can sort of look inside this small Mandelbrot set and look at the small Mandelbrot set inside of it, and then look at sort of zoom in on that small Mandelbrot set. And so here, right, these combinatorics would correspond to, in both of these small Mandelbrot sets, I'm taking the same small Mandelbrot set, right? So this would correspond to seeing the same small Mandelbrot set appearing twice in a row in our sequence. And so this, if I were to keep doing this, sort of taking this version of the small Mandelbrot set at each stage, so then I look at this one, and then here I look at the corresponding one here, right? These small Mandelbrot sets, this would give me, if I pick the same one, then my list would just be repeating the same small Mandelbrot set over and over again. And so this is an example of bounded combinatorics, which is just requiring that the sequence of small Mandelbrot sets that I'm pulling out my quadratic-like or hybrid conjugates of my quadratic-like restrictions, I'm just requiring that these are all, this gives me some finite list. So I'm not taking sort of arbitrary combinations. And it turns out that sort of bounded type combinatorics has been easier to understand. And so and just to go back to the rigidity that Mitsu had mentioned earlier, the idea is that you want to, the rigidity statement that Misha shows in the secondary limbs, when you have the secondary limbs condition and you have a priori bounds, is that if you have combinatorial equivalence, so if you have two infinitely renormalizable maps which have the same combinatorics, this list is the same, then you can upgrade that into quasi-conformal equivalence. And upgrading that into quasi-conformal equivalence gives you this form of rigidity. And it turns out that once you upgrade to quasi-conformal equivalence, you can upgrade that into conformal equivalence, and to say that the polynomials have to actually be the same polynomial. And so this rigidity that you get gives you MLC. It turns out MLC is the same as just saying, right, that the nest, if you look at these small Mandelbrot sets, these are giving us, for an infinitely renormalizable polynomial, you have some infinite nest of small Mandelbrot sets all contained in each other. And MLC is just equivalent to knowing that all of this nest is shrinking down to a single point. And that's exactly where the relationship, you can show just directly that these are equivalent. And so the rigidity that you get going from first combinatorial equivalence all the way up eventually to conformal equivalence implies MLC directly. All right, and so to list off a couple of MLC, I guess before I list off some results, I wanted to use this to talk about the secondary limbs condition. And so once we have our combinatorics, we have this list of small Mandelbrot sets. This satisfies what's called the secondary limbs condition. If all of these small Mandelbrot sets belong to some finite collection of truncated secondary limbs. Where inside the Mandelbrot set, a limb, I guess to go back to the picture of the Mandelbrot set, we have this main cardioid in the center here, and a limb is all of these decorations directly attached to the main cardioid. And if you look at attached to this cardioid, these give you your limbs, and then attached to each inside each limb, there's a main hyperbolic component, which is almost a circle. In this case, at -3/4, it is actually a circle. And so all of these small hyperbolic components, they are decorated by what are called secondary limbs, or you have our cardioid, which has attached to it limbs, and then attached to the main hyperbolic components there are the secondary limbs. And so the truncated secondary limbs is just destroying or removing some neighborhood of the attachment point, which is also called the root of the secondary limb. And so as long as our small Mandelbrot sets are contained in finitely many of these truncated secondary limbs, then we're happy. Then this is exactly the secondary limbs condition, which Misha established, which combined with a priori bounds gives us MLC. And this truncated secondary limbs condition, this is sort of immediately satisfied for any bounded combinatorics, because if we have bounded combinatorics, we're only considering some finite collection of small Mandelbrot sets. And when we have a finite collection of small Mandelbrot sets, they automatically will belong into finitely many secondary limbs. All right, and so now with this, I want to talk a little bit about some MLC results which have been already established. And so with specifically producing a priori bounds, one of the first major results was by Jeremy Kahn in the 2000s, where he produced a priori bounds for all bounded primitive combinatorics. So for any combinatorics where where all of your renormalizations, all the small Mandelbrot sets you're considering are primitive, and we're also in the bounded type case, so we just have our list is just a finite number of primitive small Mandelbrot sets. Jeremy established local connectivity or a priori bounds, and hence local connectivity due to Misha's result in this case. The next case that was then handled was by joint work with Jeremy and Misha, where they handled what are called all definitely primitive combinatorics. Sometimes it's also called the molecule condition, but now they've started to call it the anti-molecule condition. And so the definitely primitive combinatorics, these are all primitive, but we want our combinatorics to be getting, we now are allowing for unbounded primitive combinatorics, but we want all of our small Mandelbrot sets to be staying sort of definitely away from the satellite combinatorics. And just to give a picture of this, if we have this Mandelbrot set here, the main molecule, we can see we have our main cardioid, which has several hyperbolic components attached to it. And then those hyperbolic components have several hyperbolic components attached to them, and so on. If I keep just taking by direct bifurcation, going from the main cardioid and extending out, this will give what's called the main molecule. And the definitely primitive condition is just ensuring that all of the primitive small Mandelbrot sets that you get in your combinatorics avoid some definite neighborhood of the main molecule. And so, right, the main molecule, these bifurcations are exactly satellite bifurcations. And so what we need to establish for the Jeremy and Misha result is that as long as we really stay definitely away from satellite, as long as we're definitely not doing anything even resembling a satellite renormalization, then we're happy. And so this, which I'll just call definitely primitive, but they call the molecule condition, or sometimes it's called the anti-molecule condition. So this really sort of showed that as long as you are studying just primitive combinatorics, it's manageable, and really sort of hinted at the fact that the satellite case is much more complicated and much harder to study than just the general primitive setting. Because exactly, even having primitive that's resembling satellite or getting close to satellite gives some obstruction. And so after this work, there's some other results which I haven't listed here, but other interesting results that I wanted to mention are for some unbounded satellite combinatorics. So there's a result by David Chergui and Mitsushi Shikura, and then results by Dima Dutko and Misha Lyubich, producing a priori bounds and MLC, or I guess producing at least MLC for some of these unbounded satellite combinatorics, where you have infinitely many small Mandelbrot sets in our list, but they're all satellite. But in particular, these examples use a different kind of strategy. They don't establish a priori bounds explicitly in the same way that the other results have. And in particular, in the unbounded satellite combinatorics, a priori bounds, at least as I've defined them here, fail. You can show that in the examples that Davoud and Mitsu study, you generally shouldn't expect there to be any kind of a priori bounds. These quadratic-like restrictions, these renormalizations are really getting very, very small modulus, and there's no hope of getting any definite control of the modulus. But in some examples, in particular the near-parabolic setting, or in the near sort of Siegel setting. So the near-parabolic setting was by Shergi and Shishikura, and then the sort of near Siegel case was handled by Dudko and Lyubich. In some settings, in some cases, using sort of more sophisticated renormalization techniques, using the Inu-Shishikura renormalization in the near-parabolic setting, and using this Pac-Man renormalization in the Dudko-Lyubich case. And so these are sort of a different strategy, and also very sort of very sophisticated, and not like a different approach than just proving rigidity directly through a priori bounds. And so the satellite case still from these appeared to be much more difficult to understand. The other cases are sort of handling very large, broad classes of combinatorics. But these unbounded satellite combinatorics require some very careful control of how you're picking your combinatorics. But then very recently, Dudko and Lyubich, Dima and Misha have produced a priori bounds for all bounded combinatorics, including satellite combinatorics. And so with this, it really sort of has shown that the satellite case is maybe not, even though it's more complicated than the primitive case, there's some hope of actually being able to study it and being able to prove directly a priori bounds without having to go to some other kind of renormalization scheme is also sort of a very, very promising result in trying to establish a priori bounds or produce MLC in more general contexts. And so the results that Jeremy and I have been working on is what we've been calling sort of parabolically bounded combinatorics, which I'll give a definition of what that is precisely. But the parabolically bounded is something which will be still bounded in some sense, and specifically, these will be parabolically bounded primitive combinatorics, but these will fail the definitely primitive setting, right? So these will be combinatorics where now our small Mandelbrot sets are approaching and resembling something satellite, but not but still have some kind of bound that will allow us to produce a priori bounds.
Alex, can I make a quick comment?
Yeah.
I think for item number 3, the result using Pac-Man gives us examples of bounded satellite combinatorics, not unbounded.
Actually, yes, I think you're right. Thanks, Will. Yeah, sorry, that's a good point. The Shergi Shishikura result is unbounded satellite combinatorics, and the Dudko-Lyubich gives bounded satellite combinatorics. Thank you, but still, these require some sort of careful figuring of your careful positioning of your combinatorics, and the bounded type case has since been resolved in complete generality by Dudko and Lyubich. All right, and so in order to define this parabolically bounded setting, I want to look at if we have a quadratic-like map, its filled Julia set can be divided into what are called limbs by the alpha fixed point. And so here there's sort of 2 fixed points. Any quadratic polynomial will have 2 fixed points unless it has z squared plus a quarter. And so it'll have 1 fixed point which sort of lives in the middle of the quadratic polynomial, or the filled Julia set. The other, which is called the beta fixed point, lives out here at the end. And so this alpha fixed point is also sometimes called the dividing fixed point, because when I delete it from the filled Julia set, I split my filled Julia set up into multiple pieces, as opposed to the beta, which doesn't divide the filled Julia set. But the dividing fixed point, this alpha fixed point, will cut if I remove it, the corresponding components of the filled Julia set are called the limbs of the filled Julia set. And the action of F restricts to, it maps these limbs according to some rotation, to some translation, if I label them according to the counterclockwise ordering. So like this is the 0 limb, this is the 1 limb, 2, 3, 4. And here, I guess I meant to put it in here, but we need to be a little bit careful in the case where J is equal to 0. But in general, right, if I look at, this is the 1 limb, which is being mapped over to the 3 limb. This is the 3 limb, which is being mapped to the 5 limb, which is being mapped to the 2, and then the 2 is being mapped to the 4. So this gives an example of a combinatorial rotation number of 2/5. Where here just, it looks like we're doing a 2/5 rotation around this alpha fixed point. And so the setting that Jeremy and I have been studying, which is called this which we call parabolically bounded. So here, what we require is that for some bound, which I'll call B, right, we have a quadratic-like map, which is renormalizable, and I just want to call this script K to be the union of all the small filled Julia sets corresponding to the renormalization. So my quadratic-like renormalization will give me some small filled Julia set, but when I map it around, this will map around the filled Julia set and give me some cycle of small filled Julia sets. And the full union of the cycle is what I'm calling this K. And so the setting that we've been studying is where the combinatorial rotation number is given by 1 over Q. Really, you can do it for more general combinatorial rotation numbers. Like if you have something like 1 over Q converges to 0 when Q goes to infinity. If you have something that converges to say a half, you can do something similar, but it's a little bit, you can write it down with continued fractions. I don't want to get into it too detailed. But so yeah, we require the combinatorial rotation number in this case to be 1 over Q. And then I want the number of components inside each limb to be bounded by some number, which is at most B. And then I want here, going back, I want every component inside the 0 limb to be mapped into some limb, which is at most distance sort of B3 away from the 0 limb. And to look at the picture of this, right, the idea is that, as I mentioned, these limbs, the 1 limb maps to the 3 limb in this picture, the 3 limb maps to the 5 or the 0 limb here. But the point is that the 0 limb doesn't map just to the 2 limb here. The 0 limb will have one piece which maps to the 2 limb, but then it'll have other pieces that map to every other limb. And so the 0 limb can map anywhere into the filled Julia set. And so I want to know that the small filled Julia sets inside the 0 limb don't map don't map sort of too far away from the 0 limb. And the note here is that in particular, the case where B is equal to 1 or B2 is equal to 1, where the number of components inside each limb, I guess more specifically, each limb which isn't the 0 limb is at most 1, was first studied by Jeremy and Misha several years ago, and they have an unpublished manuscript on this, but they sort of worked on it and thought about it and then couldn't come up with this sort of more general setting and put it to the side. And then recently, Jeremy and I have sort of picked it back up and been able to modify. So not all of their arguments can be modified when you have the case where B2 is equal to 1. And so we've had to come up with some new arguments to handle this case. But we've sort of gotten it for as long as our combinatorics are bounded inside the number of small Julia sets inside the limb are bounded by any number. And to give another example or a picture of this, right? So here I have this small Julia set corresponding to some renormalization, which is being mapped. And here all my combinatorial rotation number is all 1 over Q. So I'm just marching along counterclockwise in all of these. And so this this small filled Julia set is being mapped here, which is being mapped over here, back, and then here into the 0 limb. And this small Julia set inside the 0 limb is being mapped here. And so here we can see that inside each limb, I have at most 2 small filled Julia sets inside the limb. And in this case, all the limbs in the 0 limb are being mapped into the 0 or the 1 limb. And so this would give me something which is parabolically bounded for a bound, I think, 2 in this case. Here's another example where it's a little bit more complicated, where I have this small filled Julia set, which is sort of marching around It's marching, passing around, coming out, and mapping eventually back into the zero limb, which is mapping forward, and then again, sort of marching back around, eventually back here. In this case, we see that we have two, at most, I guess, in the zero limb, we have three. Otherwise, we have two small field Julia sets inside each limb. And if I look at the small field Julia sets inside the zero limb, these are being mapped either into the one limb or into the zero limb. And so this will give us, again, a parabolically bounded, the parabolically bounded setting for some bound, I guess here, B will be 3. And the point, the sort of crucial point in the parabolically bounded definition is that we aren't requiring any control of Q. We're just saying as long as we have Q can be whatever it wants. So there's lots of different combinatorics, lots of different small Mandelbrot sets this can correspond to. All we require is this bound sort of per limb and what's happening per limb, but the number of limbs can be arbitrarily large.
Alex, I have a question.
Yeah.
So can you describe this parabolically boundedness as a location of the small Mandelbrot set?
Yes. And so an alternative way of describing this location is we can look at so if I have these limbs, in particular the 1 over Q limbs, there's a construction of Branner and Dewey embedding these limbs in the Mandelbrot set into the next one. So if I have here, this is the 1 over Q limb for some large Q, and I can map it in, I can embed it into this one continuously, respecting the dynamics. By some embedding described by Branner and Dewey, and I can map that again into another one, and then I can map that again into the next one. And so one way of describing the parabolically bounded combinatorics is by saying, if I start with some small Mandelbrot set in some 1 over Q limb and push it forward through these embeddings to get now an infinite collection of small Mandelbrot sets, one inside each limb, right? The parabolically bounded setting could be also requiring just that my combinatorics, if I look at the set of small Mandelbrot sets inside my combinatorics, these is just contained inside some string given by this, or some collection given by pushing forward by these Branner-Dewey embeddings. So in particular, as an example, we can look at the sort of this small Mandelbrot set given here, which is corresponds to the airplane in the 1/2 limb, or the Cocopelli in the 1/3 limb. But then this will map forward to another small Mandelbrot set, which we give here. And then this one, when we map forward, will give us another small Mandelbrot set here. And this will give us another small Mandelbrot set here. And so our parabolically bounded, one example that it handles is as long as our small Mandelbrot sets are contained in any of these, any of the small Mandelbrot sets in this sequence of small Mandelbrot sets. So I could take this one, I could take this one, I could take this one, I could take one sort of a billion closer towards a quarter down to the left. But as long as I'm picking out from this finite list, in this case, the list is, I guess this infinite list given by sort of one string of small Mandelbrot sets, then I'm happy, and this satisfies the parabolically bounded. And in particular, we could take any finite collection of small Mandelbrot sets and push them forward. And as long as we take some finite collection and then push them forward, we're free to pick inside that sequence. And so anywhere inside that sequence. So we can also view it as just imagining that inside, this small Mandelbrot set, I just am taking we can imagine being agnostic to which limb I'm in, but inside each limb, I'm just picking out some finite number of small Mandelbrot sets. And so that's sort of where the bounded is, and the sort of parabolically bounded is describing the fact that we don't really care which limb we're in, as long as we're in one of these 1 over Q limbs. All right, and so that gives sort of another characterization of this parabolically bounded, really in terms of the location of these small Mandelbrot sets. And so I don't want to get too detailed into the proof, because unraveling sort of the proofs of these things it takes a lot of construction. But just to give an idea of what we're doing, an idea of we're really building off of the theory first established by Jeremy Kahn and then further developed by Jeremy and Misha, and then now Dila and Misha as well. So for the bounded primitive combinatorics, Jeremy established these a priori bounds using sort of an optimism principle, sometimes called a life improvement principle, which I've given sort of very sketchily. This isn't fully technically correct, but morally it's correct, which is that if we have some quadratic-like map, which has bounded primitive renormalizations, so that's infinitely renormalizable with some sequence of renormalizations like this, the life improvement principle, or this optimism, is saying that if I have the modulus here, which is sufficiently small, so if I have some very bad modulus, and here really I mean that there's no way to improve the modulus, sort of the soup of all the moduli that I could pick for this renormalization is sufficiently bad, then that forces the modulus at some earlier stage, at some lower level of renormalization, to be even worse, and there's no way to make it better. And so this is oftentimes sort of just described as bad now, worse earlier principle, right? Which is saying that if the modulus is really bad now at some level, then it was even worse at some earlier level, right? So if it was bad now, it was worse yesterday or sometime previous. And with this sort of life improvement principle, you can see this will immediately give a priori bounds, just because if I can continue, if my modulus is getting worse and worse and worse, then I can use this to keep pushing it back to make my initial modulus arbitrarily bad, but my initial modulus is a number, and so it can't be arbitrarily close to 0. And so this will give you a priori bounds by running it through this sort of life improvement principle. In the bounded satellite case, the sort of what Misha and Dima do in order to control the satellite case is they show that when you allow satellite renormalization instead of just considering primitive, you get a new possibility which arises, which is sort of a pessimistic principle, which is saying that if you get very, very bad modulus, if your modulus at Gn is still very bad, then now the modulus at the next stage has to be much worse. So in this case, it's sort of a pessimist. If it's bad now, then it'll be much, much worse tomorrow. And they show that if once you start this, your modulus has to be getting worse and worse and worse, and start getting worse sort of exponentially or super exponentially fast. But in the bounded type case, the moduli can shrink only at most exponentially fast. And so this will give you a contradiction to get a priori bounds. And what Jeremy and I do is, instead of looking at sort of a pessimistic principle, we're much more closely related to this optimistic principle that Jeremy produced in the bounded primitive case, which is mostly coming from the fact that we're still considering only primitive combinatorics. And so we get, just to give it a little bit more precisely, we have like a super optimism principle. So we have some quantifiers, but the moral is that what we show is that in the parabolically bounded case, if you have some bad modulus, if I have some quadratic-like map, which is renormalizable, and my renormalization has particularly bad modulus, then the modulus of my original map has to be, in this case, I can force it by increasing Q. I can force it to be sort of arbitrarily worse than the one that I started with. And so now it's not, if it's bad now, it was a little bit worse earlier. If it's bad now, then it was incredibly worse before, which is here a little bit more powerful, which in terms of combining the different results matters, but for our purposes, it's sort of a high level. Morally, you get a priori bounds in the same way. And here I just want to note these parabolically bounded combinatorics. So these, because I am looking now at small Mandelbrot sets from an infinite collection of limbs, these very specifically do not satisfy the secondary limbs condition. They were picking them sort of very immediately from some infinite collection of secondary limbs. And so there's no hope of getting the secondary limbs condition. And so Misha's result saying that a priori bounds gives you MLC doesn't follow immediately in this case. So there's a little bit of extra work that you need to do in order to improve your a priori bounds into MLC. And this, there's a little bit of technical working. Jeremy has a different condition than the secondary limb condition, which you can use. And then by adjusting some of the work that I did in my thesis, you're able to show that in this near parabolic setting, you can improve your a priori bounds to MLC, but I don't want to get into it because that's really sort of another story. And just to end by giving like a very, very brief idea of where this life improvement, where these results are coming from and what sort of analysis they were doing to get them, right? All of this, all of these examples come from studying the near degenerate regime, right? Which corresponds to looking at if I have some quadratic-like map, right? So I have some domain, some disk V with small field Julia sets inside of it, and I can cut out these small field Julia sets to get some Riemann surface. And basically the near degenerate regime, I want to study how this Riemann surface can degenerate. And so we can imagine, like look at families of paths which have very large extremal width, which is also sometimes called modulus, or which is just the reciprocal of the extremal length, right? And so here, these very, very wide path families would correspond in this picture to these, like in this small field Julia set, to being very close geometrically to the boundary here, right? So these things are very close together, which will give me some very wide path family. And these wide path families have to respect something of our dynamics. We have some map acting on these small field Julia sets, which is going to move around these wide path families. And basically the whole game is looking at how these path families are being forced to intersect, but they aren't really allowed to intersect if they're very wide, and also applying the Grich inequality to understand how the dynamics influences what the dynamics forces some sort of restriction on these path families. And what you get is you can show in, say, the bounded type case that if I have lots of degeneration, so if I have very wide path families, then most of the generation, or at least some definite part of the degeneration, has to be vertical, sort of connecting to the outer boundary, right? And we can observe that, right, all of these wide path families correspond to degeneration, which will prevent me from having large modulus for my renormalization, right? If these small field Julia sets are very close together, then the modulus around this small field Julia set can't possibly be very big. But the vertical degeneration corresponds to, because these small field Julia sets are inside sort of our bigger original field Julia set, vertical degeneration connecting these field Julia sets to the outer boundary will also prevent the original map from having too large modulus, right? If this is being connected very close to the boundary, then there's no way to draw a very wide annulus that goes around the whole field Julia set. And so the whole game is to just trying to establish that when you push around these wide path families and you act on them by the dynamics, you want to just observe that actually most of the generation has to be vertical, and you can't just have a lot of horizontal or a lot of degeneration connecting these small field Julia sets. And that gives you the sort of, if you have bad degeneration for your renormalization, then you also have bad degeneration. And in this case, in some cases, or in most cases, even worse degeneration for the original map. And our argument is just exactly the same tools. We're doing exactly the same thing. And the sort of main observation that allows us to still control what's going on in this setting is the fact that in the parabolically bounded case, our dynamics, we now have an infinite, or I guess unbounded topology for our Riemann surface. But the point is that our dynamics sort of near the alpha fixed point, we're going to see a lot of place where our dynamics isn't doing anything interesting. And just to look at the picture that we had before of the parabolically bounded, here we have some dynamics, but sort of around the alpha fixed point over here on the right, we get a region where our map is acting, essentially, it just looks combinatorially like a translation. And this very simple combinatorics allows us to try and sort of ignore the unbounded part aspect of the topology, the fact that we have some unbounded number of limbs. We can try and come up with, basically our whole argument is figuring out how to ignore the dynamics inside this this region where we're acting like a translation, to say that we are close enough and similar enough to the bounded type case that we can just apply the bounded type arguments to get a priori bounds. And so sort of very, very briefly, that's the idea of what we're doing. And I will end there.
Yeah, thank you very much. Let's thank Alex. And let me open the discussion. Any comments or questions? Yeah, Mitsu.
Oh, you're muted, Mitsu.
Yeah, you're still muted, Mitsu.
In your definition of a parabolic B-bounded, you restrict it to this 1 over Q limbs with a Q arbitrary.
Yeah.
But can you do all the rational numbers considering the continued fraction expansion of a rational number?
Yes. So if you look at if you allow the continued fraction expansion to just have, if you just bound the length of the continued fraction expansion, then everything is the same. And so that's fine. As long as you aren't becoming irrational, then you can handle it. And so anything approaching any rational number is fine.
Another question is that in the final statement, maybe you can show it. So you're bounding the modulus for the previous step, given
Yes.
the modulus for the R of F. So you mentioned that the modulus is not uniquely defined. So there's a choice of domains and so on. So how do you?
Yeah. So here I
deal with it?
mean more carefully. If here I really am talking about like the soup. Yeah. So if the soup of all possible choices of restrictions of modulus for the renormalization is small, then that forces my renormalization of the original, whatever original one I started with, that forces the renormalization, or forces the original one to have bad modulus. But here, really, I mean, like I really want to say like there's a soup over all possible choices of domain for this renormalization, or the modulus
Okay,
renormalization.
Thank you very much.
Are there other questions or comments?
Can I ask one?
Yes, sure.
So Alex, so
I'm not quite sure how to help you with that.
think about this infinitely renormalizable polynomial whose combinatorics is 1 over Qn, such that Qn goes to infinity. So is it covered by your theorem?
Yeah. So you said infinitely renormalizable primitive with 1 over Qn.
It's not primitive, it's satellite. It's 1 over Qn,
Yes.
right?
So the satellite case we do not handle. It might be possible to take our arguments and try and combine them with these results of Dudko and Lyubich to get a statement for the unbounded satellite in this case.
Do
But
you only handle primitive types?
yeah, so here, yeah, sorry, I forgot to put it in here, but the parabolically bounded, I want the parabolically bounded to be primitive. Yeah, sorry, I forgot to put it in here, but this should be these. We really here are only considering primitive combinatorics.
Okay, thanks.